Okay, what I'd like to do today is I would like to go over how to create a binary tree with an array. We'll be working through the exercises for lesson 6 and getting our solutions ready. All right, so our first problem says represent a binary tree for integer values using an array of type integer with a length of 100. We're going to leave the elements in the array null. Remember that while an array of type int will start with default values of 0, an array of type integer will fill with null. Note we talk about nodes in the tree, but you do not need a node class for this. Simply place ints in an array. Okay, so first off, I've got a project called Array Trees. I want to go ahead and just look at this. If I say integer r array r equals new integer 4, let's take a look at R. Let's take a look at it and see what it looks like. So you'll notice that the values that are stored there are null. This is really different than if I have int array R2 equals new int 4. This is very different because this is an array of primitives, okay? Now remember, all arrays are reference types, or what they say here, object references. But what's in the object reference is different. So you'll notice that what's the reference points to a specific spot in the memory, and then we're writing directly on there the number 0. Whereas in an array of reference types, we have an array of references, but these are null, so they're null references. So big difference there between storing 0 and storing null. All right, let's go ahead and make our class. It's going to be, we need to be making a binary search tree with an array. So I'm just going to call this binary search array. No, that's not a very good idea because that sounds like something else. Binary search tree array, or BSTA. All right. So we'll just close out all this. All right. And we're going to say public class binary search tree array. And I'm going to have this made with an array, not a linked data structure. So I'll say private integer array. And upon instantiation, we're simply going to make this array into a new integer type of size 100. So when we have a length of 100, that's going to put a limit on how big our array can be, on how big our binary search tree can be. We could write an expand method that copies over and expands it, like we've done before, but we're not going to be doing this now. We're going to be limiting the amount of memory that we can hold. And that could be for many different reasons that we want to limit the memory. Lots of microcontrollers are appearing in different things. These smart dishwashers, smart whatever. They might have something like a binary search tree in them, but they have a limited amount of memory. So that's just one little thing there. Okay, so we're going to write the add method. Public void add, and we're going to be adding the integer x. Well, in order to know where to add, we're going to need to be able to search this tree, right? Was it, we should. Do we have a size? Like, I don't know if we need one. Yeah, no. We're going to start searching. So let's review how we search a binary tree. All right. So when we search a binary tree, we usually start at a root. So let's say we had like a 12 here, and then we had another number here like a 7. Maybe another number here like an 18, because it's a search tree, it'll be in order, okay? And then this will be like a 14, and maybe this will be a 9, might even have a 10, and this might be a 3. And let's pretend that we wanted to add the number 8. I think that was supposed to be at 13. All right. So if I want to add the number 8, I would start here. Okay. And I would compare my object that I'm trying to add to that. Well, we're using the abstract data structure. See, this is the abstract. It's not necessarily the concrete data structure. It's not what it looks like in our computer. This is how it behaves. The way we're doing it in a computer is we're using an array as opposed to linked data structures. We're using an array. So the first thing that I'm going to be doing, and it's going to be in that order. It's going to be in level order, okay? The first thing I'm going to do is compare it to index 0. So that's where I'm going to start. All right, so I'm going to say int current. We've usually set current to a node, but we're going to be setting it to an index. Okay? Now, if the current node if the root node is null, then we know that this tree is empty. So we could even check that before we say current equals 0. In fact, I'll do that. Well, we'll do it right here. But we need to check that. That's part of adding to a binary search tree is checking the root. So if my array bracket current is null, that means there's nothing in the tree. Tree empty. Okay, if the tree's empty, then no matter what we're trying to add, that becomes the root. So we'll say array bracket current is equal to x. We're just adding that value directly. Okay, else we're going to do something else. Okay. We'll say that I'm going to say while my current index is less than 100. If x dot compare to array bracket current is less than 0, remember objects you have to use dot compare to. I cannot use the less than sign for this. Current is a primitive, lowercase int, right? And I'm just checking if it's less than 100. But x is a capital integer. I have to use compare to. I cannot use int, or else you're comparing their reference locations, not the values themselves. So dot compare to, if it's less than 0, what that means is x is less than the value of array current. Then what I need to do is I need to move to the left child. Okay? So I'll say then current is equal to current times 2 plus 1. Because the child is always of an index twice the parent plus 1. This is index 0, 1, 2. 0 times 2 plus 1 is the left child. Look at this one. Its left child is at 3. 1 times 2 is 2, plus 1 is 3. This left child here, whatever it would be, 3, 4, 5, 6, 7, it would be 3 times 2 plus 1. Now, there's a couple things we need to make sure. I need to make sure that my new current value is not outside of the range. So I'll say if current is still less than 100 and that value is null. If that value is null, then we have found the empty spot in our array, and we'll say array bracket current gets x. So we're assigning the left child. Else, if, we said less than, I don't know if we want to allow duplicates. Did it say in our instructions to allow duplicates? Probably didn't tell you. Um, let's go ahead and just slide duplicates to the left. I think that's kind of the norm uh, when you are allowing duplicates in a binary tree. Oops, I'm missing an equal sign here. So we'll just, so if it's equal to, remember, if dot compare to gives you 0, that means they're equal. So we'll say else if x dot compare to array bracket current is greater than 0, then we'll say, well, you need to equal the right child, which is times 2 plus 2. Now we're going to see if that new spot is null. Again, we need to make sure it's less than 100. If it's not less than 100, it's going to break the while loop on the next iteration, by the way, if you didn't notice. And array bracket current is equal to null. We'll say array bracket current is equal to x. Okay. Now, there is a little bit of an issue that we need to deal with. We need to deal with what happens if they try and add something and that's exceeding the max depth of the tree. So if we end up at index greater than 100, then what they've added is too many layers, and we're just not going to allow it. So we'll say illegal state exception if we get to that point. So after we add, let's go ahead and return on each one of these. Okay, that way if we end up exiting the while loop, it must be, missing a parenthesis here or here. If we exit the while loop, it must be because we exceeded that index. So we'll say throw new illegal state exception. And I'll say max tree depth of 8 exceeded. All right. And I think it's java.lang, so we shouldn't have illegal state exception. So I don't think I have to import that. I think that's just java.lang. All right, so that should take care of the add method for us. Next, I've lost my instructions here. Let's write contains. So we'll write the contains method. Public Boolean contains. And we're looking to see if it contains some integer x. Remember, don't use equals equals with objects. So we'll say int index is equal to our int current. We'll start at 0. Okay. And then what we're going to do is we're just going to do our normal binary searching. We're going to look, are we less? We go left. If we're right, if we're greater, then we'll go right. And we'll keep searching until we find that number. And if we reach a null, then we know that we didn't find it. Okay, so we'll say while current, I think we can say while current is less than 100. And current array bracket current does not equal null. No, we'll have to check for that inside anyway. I can go back and add that if I want, but I don't think I'll need that. All right. So what we need to do is see if where we currently are at is null. So if array bracket current is equal to null, then we need to return false. Else, if x dot compare to array bracket current is less than 0, current will become the left child. If what we're looking for x is less than the current, we need to slide left. So we don't say current dot left, we say current times 2 plus 1. Else, if x dot compare to array bracket current is greater than 0, then current needs to slide to the right. So times 2 plus 2. Well, what's the last thing it can be? If it's null, then we've reached an empty place and we found where we should have added it. Like if we were trying to add x, we'd be looking for the null. We're trying to see if x is in the tree. If we reach a place where it's empty, like say we're trying to add 4 here, we go left to 7, left to 3, and then we try and go right to 4. We reach null, so we know we can return false there, right? But if we this is when we slide left to slide right. So we found the node, it's just not the right node. The last thing would be if the node that we're at is actually exactly the same. Not less than, not greater than, but exactly the same, then we can return true because we found the target node. But because we have a limited depth to our tree of 100, we'll have to say, if we reach this point, we'll have to say return false. So that would be in the case that we've reached all the way through our 8 different heights of the tree, each one of those nodes being a node, and then finally we tried to go to the 9th. There is no 9th node because our array is not that big. All right, let's take a look at print level order. So print level order is very easy. Public void print level order. So to print level order, what we're going to do is simply print to the console in order from, like a typewriter. We're going to be going 12, 7, 18, 3, 9, 13, I think, and then 10. But what we need to be careful about is they're already in level order in the array. We just need to be careful to avoid nulls. So we'll say for int I equals 0, I less than array dot length I plus plus. We're going to say system.out.print. And I didn't tell you how to format it. You can do it if you want. We're going to do bracket I, and that's only if it's not null. So we're going to say if array bracket I does not equal null. Otherwise, it would literally print the word null. So there we go. And I'll tell you what, let's go ahead and do a comma like that after it. And I think I'll say, I'm doing a little bit of formatting here. I less than array. I don't know. I'd have to see. That's going to print some extra commas. So we'll just do a space. We'll just do space separated. That looks cool. And then at the end, if we, instead of printing it, if we created a toString before we print it, we could wait till the end and remove the extra comma, but I don't feel like doing that right now. And then I'm just going to close off that line by doing a blank print line to move down. Okay, so there we go. Let's test it out. We'll make a new binary search tree. Let's do, I'm going to do 12, I guess. 12, 7, 18, see what happens. So 12, 17, 18, 4, 3, I'm not exactly matching what I had earlier, 6, 10. All right, let's do print level order. So we have 12, 4, 17, 3, 6. Let's see if we can't check if that's actually correct. Sure would be nice if it were, right? Let's go ahead and take a look. All right, so our first node is a 12. Our next node is a 4. Our next node is a 17. Our next node is a 3. Our next node is a 6. Our next node is an 18. Oh, that's not good. And then a 10. That's probably not the way it is. It's probably like this, because that was probably a null. And then then we come all the way down, and then this is, oh yeah, because this would be a 10 right here. We could actually check that to make sure that we're not completely wrong by instead we could take that out and just go ahead and print it regardless. But we're gonna get like a lot of extra stuff. But that makes sense the way that would be. We could also do like a while less than size or something like that. But I'm gonna call that done. Okay. So until next time, take care.